So here's a question. We want to find the limit as x goes to 0 of x to the fourth times cosine of 1 over x. And if we do what we should do, which we should always at least think about plugging it in first, we got problems. 0 to the fourth is 0, and cosine of 1 over 0 is, I don't know. So what do? Well, typically, when I see sine or cosine of something bonkers that's not well defined, I usually think about using the squeeze theorem. Because I know, even though cosine of 1 over x, actually, if you think about what happens with cosine of 1 over x, it oscillates an infinite number of times as you get closer and closer to 0. But what I do know is it oscillates between positive 1 and negative 1. Always true. Cosine sine of whatever, always between negative 1 and 1. And then our job is to make the thing we want to take the limit of, I should say, is to make the thing that we have in the middle of this inequality look like the thing we want to take the limit of. So what are we going to multiply each part of this inequality by? Right. Negative 1 times x to the fourth is less than or equal to x to the fourth times cosine of 1 over x is less than or equal to x to the fourth times 1. And then we hope that when we take the limit of the outer parts of the inequality that they're the same. So the limit as x goes to 0 of negative x to the fourth, well, we can just plug in 0 and get 0. And the limit as x goes to 0 of positive x to the fourth is also 0. Since those are the same, we can say that by the squeeze theorem, the limit as x goes to 0 of x to the fourth times cosine of 1 over x is equal to 0. Something I've seen other people write, which I also kind of like, is some people just take this inequality and take the limit of each part. Say the limit as x goes to 0 of negative x to the fourth is less than or equal to the limit as x goes to 0 of x to the fourth times cosine of 1 over x is less than or equal to the limit as x goes to 0 of x to the fourth. This is true. If you have things that are, if you have something that's less than something else, the limit of it is less than or equal to the limit of the other thing. And then you can say, oh yeah, well, that's cool because that's 0 and that's 0. So if I'm less than or equal to 0 and bigger than or equal to 0, gotta be 0. There's no other choice. And most of the time, this is kind of how the squeeze theorem goes. You have a limit, we don't know what to do. We say, well, we've got sine or cosine between 1 and negative 1, and then we make the middle look like we want to take one of those. Yeah.
So you use the squeeze theorem when you're working with cosine and sine?
Well, so I would say that is the most frequently we usually see. So there are certainly other times you can use the squeeze theorem, but most often it is typically used when we see something with sine or cosine that we don't know how to do it. But I do have another example that doesn't have sine or cosine. Let's look at this next example. So suppose that there's a function, we don't know it, but it's less than or equal to x always, and it's bigger than or equal to the square root of 2x plus 1 plus e to the x minus 4. Now, clearly the setup here is screaming squeeze theorem, right? They're giving you this inequality where the function is between these two things. So we're being asked, what's the limit as x approaches 4? So what we're going to do is the same thing, kind of thing we did before. We're going to take the limit of the outer parts, or we could even write the other thing and say the limit as x approaches 4 of the square root of 2x plus 1 plus e to the x minus 4 is less than or equal to the limit as x approaches 4 of f of x is less than or equal to the limit as x approaches 4 of x. One of these limits is really easy to do. What's the limit as x approaches 4 of x? That's just going to be 4. And we just plug in 4 for x and we get 4. So we really are hoping that this other limit over here is also 4. Because if it's not 4, then we can't say anything with the squeeze theorem. both the left hand and the right hand thing of your inequality have to equal the same value or the same limit value when we're trying to use the squeeze theorem. It's going to be 4, but let's actually check. So when we do this limit, we're going to get the square root of 2 times 4 plus 1 plus e to the 4 minus 4, which is the square root of 9, plus e to the 0, which is 3 plus 1, which is 4. So since our limit is bigger than or equal to 4 and less than or equal to 4, it has to be true. The limit as x approaches 4 of f of x is equal. But yes, to answer your question from before, most of the time when you're thinking about using the squeeze theorem, it's usually because there's a sine or a cosine that we can't really deal with, but that we can always say is between -1 and +1. And there's not a lot of other functions we readily know that are between two well-known values. Like polynomials are unbounded, e to the x, right, could go off to forever. So there's not, right, sine and cosine are kind of, with one small exception, are really the only nice functions we know that stick between two values really easily. There are other ones, but.
You got the 1 from e to the power of 0?
Yeah.
So anything power to 0 is 1, right?
Anything that's not 0 to the power of 0 is 1. Okay. 5 to the 0 is 1, 7 to the 0 is 1, a billion to the 0 is 1, anything to the 0 is 1. And I might as well say just a tiny bit more about that, just to make sure everyone is super extra cool with that. It's just because of the additive law of exponents. So just so we all are okay. What's 2 cubed times 2 to the 4th? As a power of 2. Right, we added the exponents because really 2 cubed is 2 times 2 times 2, and 2 to the 4th is 2 times 2 times 2 times 2, and that's 2 times 2 times 2 times 2 times 2 times 2, 7 times. But that rule, which is true, means that 2 to the 0 has to equal 1. Because what's 2 to the 0 times 2 cubed? Well, what do we do with the powers? What do we do with the powers there? So what do we do with them here? Okay. So I've got 2 to the 0 times, what is 2 to the 3rd actually? Right, it's my favorite number, 8. And it's equal to, what do we have over here? Also 8. Okay, so 2 to the 0 times 8 equals 8. There's no other choice. 2 to the 0 has to be what? So that's why the 0th power of something is equal to 1, because of this additive law of exponents. It says it has to be. There's no other option, as long as the base is a non-zero number. 0 to the 0 is something that's totally different, that most of the time is 1, but sometimes it's not. So don't worry too much about that. All right. Before we talk about continuity, are there any questions for those of you, well, specifically for those of you that have a midterm coming up in 40 minutes, and if you need to leave a little early for that midterm, that's totally okay. Or just other questions. So you guys have any questions? Sure thing. Sorry. Of the second problem or the first problem? And I do post the notes in Google Drive, so if you do miss something, you can always find it later, but I'm happy to put it back up there. Yeah. Sequences. Oh yeah, we kind of, did I bring that with me or not? I mean, I can sort of think of an example, but nice to have this example there. I did not look at it fine. Yeah, so there's a lot of things to say about sequences. Whose class are you in? Okay. So guys' classes talk about sequences, and other classes talk about sequences. A little bit, okay. I mean, not that I'm like, no, but just want to kind of get a vibe here as far as sequences. So let's talk about sequences. And so in this class, we often talk about sequences before we talk about limits to infinity, because when you talk about the limit to infinity of a sequence, we're talking about what the sequence converges to. Let me grab something really quick so I can have some sort of source here. Yeah, there we go. One moment. All right. So here's a sequence. A sub n equals 2n over n plus 1. And there's a few things we can do with this sequence. We can talk about some of the terms. So usually, unless there's a good reason not to, we typically start the sequence at n equals 1. Sometimes at n equals 0, but typically at n equals 1. So I would say the first term of the sequence is 2 times 1 over 1 plus 1. The second term of the sequence is 2 times 2 over 2 plus 1. And so on. Right? The third term is going to be 6 over 4, which reduces to 3 halves. The fourth term is going to be 8 over 5. And you could do this literally forever. You obviously don't want to do it forever, but could. A question we often ask is, what is the limit of the sequence, or what does the sequence converge to? I should really say, does the sequence converge? And if so, what does it converge to? Or to what does it converge? Is probably the more grammatically correct. Not a grammar class. So when we ask these two questions, we're really just asking what's the limit as n goes to infinity? As the n values get larger, 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 does this sequence get close to one particular value? And it does. The limit here, as n goes to infinity, of 2n over n plus 1. Well, if we pick a really large, like, so, I mean, I think you guys probably know what the answer is already, but if we pick something like n equal to 999, we would see that 2 times n over n plus 1 is 1,998 divided by 1,000. That's pretty close to what number? Right, pretty close to 2. And I think we talked, now here's where I'm like, did we talk about this in the 21A class I'm doing or the 17A class? I think we talked about how to deal with limits to infinity already, where at least for a rational function, you divide everything by the largest power of your variable. Right, we talked about that? Yeah. So here I would divide everything by n. Now you can also use the shortcut, right? You say, oh, I know the degree on the top and the degree on the bottom is what? The degree is 1, so the degrees are the same. If the degrees are the same, the limit to infinity is going to be the quotient of the leading coefficients. But if someone wanted to just show work, I would say, oh, that's the limit as n goes to infinity of 2n over n over n plus 1 over n, and then I would simplify. Since the limit as n goes to infinity of 2 over 1 plus 1 over n, and then that goes to 0. So you get 2 over 1. So that's what I would do to see what that sequence converged to. A sequence really is just a function. It's just a function where we only think about the inputs as being usually positive integers. But like a function, for example, right? Here's a function we all know and love. Love might be a strong phrase, but here's a function we know anyway. F of x equals 1 over x. Looks like this. And definitely it's true that the limit as x goes to infinity of 1 over x is 0. It's closer and closer and closer to 0 as x gets larger and larger and larger. We could also talk about the sequence. A sub n equals 1 over n. And it's also true that this converges to 0. Now, the only real difference between f of x equal to 1 over x and a sub n equal to 1 over n is that for f of x equal to 1 over x, we typically think about the x values being any possible thing except for 0. So here we would say our inputs or our domain is everything but 0. Whereas for a sequence, the n values that we get to put in are usually n equal to 1, 2, 3, 4, et cetera, et cetera, et cetera. typically the positive integers. Sometimes you start at 0, sometimes you might start at -1 for some weird reason, but typically you're starting at some integer and just going to the right. So very different inputs than a function, but it still does the same thing, right? It's still taking your input and doing 1 over. So sequences are just functions with a limited domain. Let's talk about a couple more convergence types questions. Because usually, so at least as far as my imagination goes, typically the kind of questions you're asked about sequences are, do they converge? And if they converge, what they converge to. And I should look at one thing here. Okay, well, we'll talk about that in a moment here. So, a couple more examples. How about this sequence here? So then is, I don't know, let's say 3n over n squared plus n plus 2. We would like to know what this converges to. We don't, so I don't think it's particularly worthwhile to write out the first few terms. I mean, if you're asked to, obviously you should, but writing out the first few terms shouldn't be challenging, right? You're literally just plugging in values for n. So if I want to say, what the first 5 terms are, I'm just going to say, well, a sub 1 is, I'm literally just putting in 1 for n. And a sub 2 is 3 times 2 over 2 squared plus 2 plus 2. What's going on out there? So, not, in my opinion, particularly great use of our time, right? I think that's something we can all accomplish. But what about what a sub n converges to? If it converges, we're just taking a limit. Any guesses as to what this limit's going to be? Definitely going to be 0 because the degree on top is less than the degree on the bottom. And again, you could either, this is really what is your teacher going to ask you to do, right? If they're going to ask, if they want you to show work here, here's the work I would want you to show. I'm going to divide everything by the highest power of n in the denominator. I'm dividing everything by n squared. I'm going to simplify. So I think if you're dividing everything by n squared, you can skip this step and just do the simplification and say, oh, in the numerator, I really have 3 over n. In the denominator, I have 1 plus 1 over n plus 2 over n squared. And that's going to be 0 over 1 plus 0 plus 0. 0. Oh, should we look at that one? Yeah, we should look at that one. What if our sequence is alternating? -1 to the n plus 1 times 2n over n plus 1. Well, we already know that this thing here has a limit that's 2, right? That's the first one we did, I think. Double check. Can't remember even back that far. Yeah, that's the first one we did. So we know that this is going to converge to 2, but the sign's going to change every term. So what does that mean as far as convergence? Yeah, we're oscillating. So we're oscillating around, right? We're kind of going, so like, for example, if n were to be 99, I'd be getting -1 to the 100, so positive. And then I'd be getting 198 over 100. So essentially positive 2. But then for n equal to 100, I'd be getting 200 over 101, but it'd be negative, because it'd be -1 to an odd power. So that'd be essentially -2. And so we're essentially going back and forth between +2 and -2, which means we're not getting close to any one value. So in this particular one, we would say this sequence diverges or does not converge. Specifically, it oscillates back and forth, getting closer and closer to, well, that's bad language. It's not really getting closer and closer, but it bounces back and forth between numbers that are close to 2 and close to -2. Doesn't exist. On the other hand, so when can an oscillating thing have a limit that does exist? Well, what if we look at the limit as n goes to infinity of -1 to the n plus 1 times n plus 1 over 3n squared plus 5. This one's going to oscillate, but what's the non-oscillating part getting closer and closer to? If I was taking the limit of that, the limit would be 0 for sure. And 0 is the one thing that if you're oscillating back and forth between 0 and 0, well, positive 0 and negative 0, same thing. 0 is the only number that is neither positive nor negative. Really, it's its own positive or negative. So negative 0 is 0. Positive 0 is 0. But the point here is that this limit is going to be 0 because the limit as n goes to infinity of n plus 1 over 3n squared plus 5 is equal to 0. So 0 is the only one where if it's oscillating, you still get back to the equal limit. So this sequence equal to -1 to the n plus 1 times n plus 1 over 3n squared plus 5 definitely does converge. But 0 is the only thing an alternating sequence can really converge to. Kind of interesting. Yeah, let's do one of those. Okay. Let's see here. Before I get too into this, are there things about sequences? So other than talking about convergence, is there anything else we should talk about sequence-wise? I have an idea or two, but so like I said, has anyone talked about geometric sequences? Okay. So here's an example of a geometric sequence. 3 to the n plus 2 over 5 to the n. It doesn't look like your typical geometric sequence, but it is. The whole point of a geometric sequence is that each subsequent term is multiplied by the same thing from the previous term. So if I start writing out terms, my first term is 3 to the 3rd over 5. My second term is 3 to the 4th over 5 squared. My third term is to the 5th over 5 cubed, and so on. And the point isn't so much that we can see what the terms are. The point is that we can see that to get from one term to the next term, we multiply by 3/5. And that's true for every term. That's the hallmark of a geometric sequence. That each term is the previous term multiplied by the same ratio, which is 3/5. For a ratio, 3/5. Does this thing converge? Well, let's rewrite it a little bit. I'm going to rewrite it as 3 squared times 3 to the n over 5 to the n. And then I'm going to write that as 9 times 3/5 to the n. So now the question is, what's the limit as n goes to infinity of 9 times 3/5 to the n? Well, when we multiply by 3/5 every time, is our whole thing getting larger or smaller? It's a good question. Are my terms smaller here or bigger? I don't know. So when we multiply by 3/5, we get smaller. Right? You multiply by a number that's less than 1. So your overall quantity has decreased. And if you keep multiplying by 3/5 over and over and over and over and over again, your overall thing gets smaller and smaller and smaller. Another way to think about this. This is really just an exponential function. If you're going to graph y equals 9 times 3/5 to the x, it's an exponential function where the base is smaller than 1, meaning it has this look to it, where it decreases from left to right. Whereas the base is larger than 1, like e to the x, it increases from left to right. But that's telling us, oh, if that's what my function looks like, it's getting closer and closer and closer and closer to 0. which means the sequence is getting closer and closer and closer and closer to 0. So I should be a little bit more specific here. A geometric sequence, one of two things can happen. There's kind of a third thing, but it's lame. But for a geometric sequence, so a geometric sequence looks like this. It's always some constant times some ratio to the nth power. That's always how we write it eventually. And here is the deal. If the ratio is between -1 and 1, we get convergence. Technically, it could also be equal to 1. On the other hand, if the ratio is bigger than 1 or less than or equal to -1, the sequence diverges. So we already saw an example of convergence where the ratio was 3/2. Let's look at one or two more examples. Let's say a sub n was, let's say it's 4 times 3 to the n. So now, as n gets larger, what happens to the quantity here? It also gets larger, right? If n is 1, I get 12. If n is 2, I get 36. If n is 3, I get 108, and so on, right? It gets big fast. So this definitely diverges. The limit as n goes to infinity of 4 times 3 to the n is infinite. And if you had something with a negative base, it's more negative than -1, this is also going to diverge. Now this one, you can't say the limit's infinity. This one's going to be really, really like, so for example, if I plug in n equals, I don't know, 100, a sub 100 is 3 times -2 to the 100, very positive. Whereas if you plug in 101, 3 times -2 to the 101, extremely negative. This is bouncing back and forth between very positive, right? If you start kind of plotting points, it's going to start off as, negative, then positive, then more negative, then more positive, right? It's just going to keep doing this kind of crazy thing like that. But definitely diverges. There was something else here. Yeah. So the other thing you could be asked about a sequence is to find the formula of the sequence, given the terms. Sometimes it can be really easy, like, for example, here's a sequence. At least here's the first 5 terms of the sequence. What am I doing each time to get to the next thing? I'm adding 2 every time, 5, 7, 9, 11, 13, 92. So I usually think about what I'm doing to get from one term to the next term. So here, if I'm adding 2, well, if a sub 1 is 5, a sub 2 is 7, I want to think of a sub n as something plus 2n. So here's the thing you should always be thinking about. The n is always increasing by how much each time? 1, right? We're always doing n equals 1, then n equals 2, then n equals 3, right? It's always increasing by 1. N is what's called the index. It's just going to start at usually 1 and then go through the countable nice integer numbers as we like. But I want to increase by 2. So if n is increasing by 1 every time, I should multiply it by 2 to increase by 2 every time. But that's not going to be quite right, because if I just leave it like this, a sub 1 isn't going to be 5, it's going to be 2. And a sub 2 is going to be 4, and a sub 3 is going to be 6. I need to add on 3. So that now my first term works. Oh yeah, 2 times 1 plus 3 is 5. My second term works. 2 times 2 plus 3 is 7. And it works, right? Each subsequent term is going to be 2 more than the previous. So if you have the same difference each time, that difference should get multiplied by n. And then you add on a number here to kind of adjust for it. So if I had something like a sub n equal to, make it interesting, 11 8, 5, 2, -1, -4, etc. I'm decreasing by 3 each time. So I know I want to have a -3n for sure. I'm decreasing by 3 each time. And then I need to adjust. I know when I plug in n equal to 1, I want the output to be 11. So if I plug in 1, I'm going to get -3. So I need to add on how much? Because now if I plug in 1, I get -3 plus 14, which is 11. If I plug in 2, I get -6 plus 14, which is 8, and so on and so on. They get more complicated. For example, someone could say, what if my a sub n was something fractional, like, well, let's write out the terms, yeah. 1/3, -4/7, +7/11, -10/14, and so on. Well, my eye immediately sees that this is alternating. So regardless of whatever else I've got going on, I know I need a -1 to the n, or maybe a -1 to the n plus 1. One of those two should get it right. And in this case, I do want the n plus 1 one, because when n equals 1, so again, we're making the assumption that we're always starting at n equals 1. You can start at n equals 0, that's also fine. If we're starting at n equals 1, -1 to the 1 plus 1 will be -1 squared, which will start us off with a positive term. So that's what we want if we're starting with a positive. If it was starting with a negative, we'd want that instead, because that will start us off with a -1 when n is 1. And then I'm going to look at the numerator and the denominator separately. The numerator is increasing by 3 each time if I ignore the negative signs. So my numerator, I need a 3n plus or minus something. My numerator, sorry, my denominator is increasing by 4 each time. So I need a 4n. And when I plug in n equals 1, on top I want to get 1, but I'm getting 3. So what do I need to do? Subtract 2. And in the denominator, when I plug in 1, I get 4, but I want to get 3. So I need to subtract 1. And then I need the -1, the n plus 1. And that would be the formula for my sequence there. And sure, a couple other things that might come up. So sometimes the patterns are not so straightforward. For example, we might have something like the following: -1/4, positive. So I'm not going to be cruel. A cruel person might write 1/3 here, which is the reduced version of 3/9. You'll see why that would be mean in a second. The next one's, what's that? Yeah. So the next one's -27/16. The next term is +81/25. So does anyone notice anything about the terms of the denominator? They're all perfect squares, right? This one is 2 squared, 3 squared, 4 squared, 5 squared. But if I'd written that one as 1/3, it would be harder to see that. So it's looking to me like the denominator is, if I start at n equals 1 and I get 2 squared, I'm going to want an n plus 1 squared. Because again, right, each of these, this is just increasing by 1 each time, and I'm squaring it. So I want that to be an n, but it can't be just n because n starts at 1. My numerator, what's my numerator looking like? 1, 3, 27. I feel like I'm missing a number there. Yeah, I think I made that was a mistake there. That's all right. Sometimes mistakes happen. So really this shouldn't be, yeah. So I'm going to show you how this is wrong. 1 is 3 to the 0. 3 is 3 to the first. 27 is 3 cubed. 81 is 3 to the fourth. That's a problem though, right? Because I missed 3 squared. There's nothing to do with this. This is a mistake. So what the person who wrote this probably actually meant to write was the following instead. -1/4, positive 3/9, -9/16, positive 27/25, and then maybe a -81/36. That's actually what we're looking at, because then we still have our denominator being what we already determined it was, n+1². And now our numerator does look like nice powers of 3, right? That's going to be 3 to the 0 over 2 squared, and 3 to the first over 3 squared, and 3 to the second over 4 squared, and 3 to the third over 5 squared, and 3 to the fourth over 6 squared. So we could write the numerator as 3 to the what? N -1, right? Because if we do n, we're starting at n equals 1. But I want to start with the power of 0. So when n equals 1, I need an n -1 to get the power of 0 there. Sometimes when people are writing these, they say something like n greater than or equal to 1 to make sure we know we're starting at 1. And then we also have the alternating part. Now, I could just maybe stick the -1 on the 3 since it's already being raised to a power. The only issue is, am I going to get the right sign when I start off here? If I plug in n equals 1, am I going to get a positive? Is my first term going to be negative? Nah. Right? Because I'm going to get -3 to the 0th power. And what's anything to the 0th power? 1. Even if it's a negative quantity to the 0th power, it's still got to be 1. I should point out, because it does come up on occasion, -3 to the 0th power is 1. -3 to the 0th power is -1. Because here you're doing the power of the whole thing. Here you're doing the power of 3, and then it's a negative of that. Order of operations, right? We do powers, we do exponents before we do subtraction. So this is not quite right. What I really should actually have is just multiply this by a -1. There's other ways to take care of it. You could definitely write it as -1 to the n times 3 to the n -1 over n + 1 squared. It's probably better. Okay, well, it's 2:50. You might as well save the continuity discussion for next time. Question? Oh, no, not a question. Sorry, you look like you're raising your hand there. The last, well, not the last, but one more sequence thing. Recursive sequences. So a sequence that's defined in terms of itself. Something like a sub n + 1 equal to 1/2 times a sub n + 5. And typically, when you're given a sequence recursively like this, you have to be given a starting point. So we're going to start with our first value, a sub 1 is 4. And now the question is, I mean, there's a lot of questions, but the question we really usually care about with a question, a sequence like this is, does it converge? Well, let's see what happens if we plug in a few values. A sub 2 is going to be 1/2 times 4 + 5. I'm just plugging in a sub 1 to get a sub 2. And that's going to be 1/2 of 9, which is 4.5. And then a sub 3 is going to be 1/2 of 4.5 + 5, which is going to be half of 9.5, which is 9.5. Half of 9.5 would be 4.75. And then a sub 4 would be half of 4.75 + 5, which is going to be something terrible. I think 4.875. Yeah. It definitely looks like we're getting closer and closer to what? Maybe 5, right? I mean, maybe not 5, maybe it's like 4.9. I don't really know. Not that very good. But the idea here is that we can kind of see, well, it looks like we're getting closer and closer to something. So if this were to converge, meaning if we were to get close to one particular value, if it converges to that value, then if we plug that value in, we should get that value back. So let me ask you, if you plugged in 5 for a sub n, what would a sub n plus 1 be? It would be 5. And if you plug in 5, 1/2 of 5 plus 5 is 5. 5 is what's called a fixed point of this recursive sequence. How do you find it? You find it by setting both of these a sub whatever is equal to whatever variable you want to call it. The typical choice is capital L, because we're often thinking of it as the possible limit of the sequence. So the way we find the fixed point of this sequence, or fixed points, I should really say, because there can be more than one, is by saying I'm going to solve L equal to 1/2 times L plus 5. I'm making the assumption that if I plug something in, it's going to give me the same thing back. And then I'm trying to figure out what that thing is. Well, it's not too terrible. Multiply everything by 2. 2L is L plus 5. Subtract L. Oh, yeah, we got 5 like we thought we would. So L is equal to 5 is a fixed point of this. I will point out, just because something's a fixed point doesn't necessarily mean the sequence converges to it. This one clearly does, right? If you start at 4, you're definitely going to get closer and closer and closer to 5. So this sequence definitely does converge to 5. What time is it? It's 2:55. If you do have a test, or even if you don't, I mean, if you want, you can always leave anytime you want or need to for whatever reason. You do not really have to tell me, like, I'm going to trust that you're leaving me because you need to leave if you need to leave. So if you got to go, you got to go. If you want to stick around, I can say more things about sequences. Good luck on your test if you have a test. Let's look at another example of this since we're here already. So we've got a sub n plus 1. Let's say it is defined recursively as the square root of twice the previous value. And we're going to start at 3. So if we start plugging in values, things get messy real quick, right? If I plug in a sub 1 equal to 3, I'm going to get the square root of 2 times 3, which is the square root of 6. Okay, that's not terrible. But then if I try and find the next subsequent term, I'm going to get the square root of 2 times the previous term, which is the square root of 6. And things start getting messy. This is about 2.45. This is about 2.21. If we do it one more time, it's even grosser. It's the square root of 2 times the square root of 2 times the square root of 6, like that. That's about 2.10. If we had to guess, we might guess it was getting closer and closer to 2. How could we actually tell that 2 might be where it's actually converging to? Well, again, we can look for the fixed points. Also called equilibrium points. So I'm going to set this thing, both of those, a sub n plus 1 and a sub n equal to L, and then solve L equal to the square root of 2L. If you look at this long enough, you might just be able to tell what the solutions are. What's one maybe easy solution that L could definitely be? I see 0. If L is 0, does that work? I'm not saying, so what I'm not saying is, I'm not saying this is the right way to go about doing it. I'm just saying that if you look at this a little bit, you'd be like, oh yeah, L could be 0 for sure. And L could also be 2. because 2 times 2 is 4, and the square root of 4 is 2, and that would be 2. But really, we should just solve this the normal way. Square both sides, subtract 2L from both sides, factor. Oh, yeah. We're getting L equal to 0, and L equal to 2. This particular one, it's definitely not converging to 0, but it definitely looks like it's converging to 2. So I would say, I would venture a guess that this converges to 0. It's up to 0, sorry. But I will point out, it's not, I'm just making this guess based on some evidence, right? But I'm actually like, there's really, and this is kind of what a lot of this course is all about, actually, is trying to show when an equilibrium is stable. Trying to show when a particular thing converges to a particular value. And so it's a ways off. Like this theme is going to carry us through 17B and 17C. Like it's gonna be there at the end of 17C. Like, oh yeah, we're trying to see when this thing converges and when this point is stable or unstable and all this kind of fun stuff. But that's the big picture. And the big picture is that it's not just enough to be like, oh well, they look like they're getting closer to 2, and 2 is an equilibrium, so it's probably. But there's a little bit more work to do there. Let's see. Oh, yeah, one more example. It's a good example. Let's look at this one. This one is kind of fun. Let's say that a sub n plus 1 equals 4 over n, sorry, 4 over a sub n. And really, you can actually start at any value, but let's start at a sub 1 equal to 1. Okay, so check this out. What's a sub 2 going to be? 4 over 3. So let me point out. So a sub 2 is a sub 1 plus 1. And it's equal to 4 over a sub 1. And that's how this recursive sequence works. You're taking the previous term and substituting in there to get the next term. So for this one, our a sub 2 should be 4 divided by a sub 1. And we're given a sub 1 equal to 1. So a sub 2 is 4. What's the third term going to be? Right, it's going to be 4 divided by the previous term. I think we're stuck. What's the next term going to be? 4. 1, then 4, then 1, then 4, then 4. Okay, so you might think, and it would be reasonable to think, that one of those values, or maybe both of them, are a fixed point. Neither of them are a fixed point. Right? Well, that makes sense. Maybe I misspoke there. You might not think that, because we know that a fixed point or an equilibrium is a number you plug in and you get the same thing back. Our fixed points here are, well, if I set both of these equal to L, multiply both sides by L, and solve, I get L equal to plus or minus 2. So this sequence doesn't converge, right? It's bouncing back and forth between 1 and 4, 1 and 4, 1 and 4, 1 and 4. You don't ever get closer and closer to either of the fixed points to a negative 2. So this sequence, at least starting at 1, doesn't converge. Now, what's interesting, I think, and I'll stop talking. Oh, I should stop talking. What's interesting is the only place you can start and have this converge is at one of the fixed points. If you start at 3, like if a sub 1 is 3, your first term is 4/3, and the next term is 4 divided by 4/3, which is 3, and the next term is 4/3, and the next term is 4 or 3, right? You just keep going back and forth between 4/3 and 4 divided by 4/3, which is 3. That's 4/3, 3, 4/3, 3, 4/3, 3, 4. It's, yeah. All right. Friday, we'll talk about continuity.